Let us move on to chapter number 2, source coding and channel coding in the framework of the course of Humming code. We'll see the difference between them. First of all, let us talk about pixelization. If we have an image like this one, this image is divided into basic elements. Each basic element, each small cell is called pixel. And the pixel has a value. If the image is colored, we'll have 3 values. If the image is black and white or from type gray, we'll have only 1 value. So if we take this part of this image, we'll see values here. To simplify the issue, I limited myself to only 8 gray labels, means from 0 to 7. So what is white for me is 7. What is dark is 0. What is in between is 1 to 6. So we have values here. So for example, this pixel is a pixel with a value 3, which is between black and white. And I represent this in the binary system with 3 digits 0, 1, 1. Because for 8 values, I don't need more than 3 bits. And if I take all values, I will find these gray levels and the values between 0 and 7. Now, I zoom this part of the image, and the situation is the following. We'll see a matrix of cells which are gray between black and white. Source code and channel code. I would like to send this image. Before that, I may do something. I may compress this image. Why should I send a lot of information? Let me compress it first. Or I can do some encryption to protect my image. So compression, encryption, all of this is called source coding. Means manipulations done at the source. And this manipulation of the signal does not have any dependence on the channel, any link with the channel. We call this source coding. It is independent from transmission, compression, encryption. For example, for a compression, I can undertake the cosine transform, which is this form here. It is complicated, we don't need to know it in details, but the main point is that this image, when transformed, it gives a concentration of information in this corner. So I don't need to send all this matrix of values. I need only to send this corner, because here there is nothing. So there is compression. In reception, of course, I will do decompression, the opposite operation. Now, errors and corrections. We go to the channel coding now. If we have a message like that one here, a sequence of bits, first of all, error is not avoidable. Whatever we do, there is imperfection in the source of the signal, imperfection in the transmission medium, and imperfection in the receiver. So whatever we do, we cannot avoid errors. This message, the message is abstract. In order to transmit this message, I have to transform this message into a signal. A signal is a voltage, for example, or is light. So for voltage, if voltage is high, like here, we have the value 1. For example, 1 volt. 0 volt means the value 0, and so on. So what is transmitted in the channel is this voltage, this curve. And this is the signal. The signal A here is ideal. Indeed, to go from 1 volt to 0 volt, you need some time. You cannot go down in no time. That's not possible in our life. So in reality, we have something different, something like this. So a sequence of pulses. And this is 1 and this is 0. And now we have to send this in the channel. That's the real signal. We have the channel here, let us say an optical fiber, and the signal should travel into this optical fiber. It goes out from the other extremity at the receiver. It goes out like this. This is very ideal because we supposed here that the optical fiber does not introduce any imperfection, which is not the case in reality. So, if there is a problem, if there is imperfection, what should we do? Anyway, in all cases, we have to use a threshold. Means we have to compare the curve with respect to a fixed value, which is in the middle between, for example, 1 volt and 0 volt, 0.5 volt. And now, when the value on the curve is higher than 0.5 volt, we say we have the bit 1. Otherwise, like here, we have the bit 0. And we can reconstruct, we can restitute our signal, which is the ideal one here. Now, what happens if there are errors? We should do some coding. So this is our bit sequence, but in reality, we have the curve that we see here, the white curve. That's a realistic curve. With the thresholding, if we apply thresholding here, we may have errors. For example, here we are supposed to have 1, but if we see the values here, they are under this threshold. Means there is an error. Now, how to correct the error? That's the subject of the next chapter. So here, 0, which is a wrong value. 1 bit is erroneous in this case. Over 11 bits, one of them is erroneous. But we don't know this at the source, and we don't know this at the destination. So we need to use an intelligent system to correct the situation. That's the subject of the next chapter. The probability error here is 1 over 11.